Machine learning is creating tremendous economic value today. I think 99% of the economic value created by machine learning today is through one type of machine learning, which is called supervised learning. Let's take a look at what that means. Supervised machine learning, or more commonly supervised learning, refers to algorithms that learn X to Y or input to output mappings. The key characteristic of supervised learning is that you give your learning algorithm examples to learn from that include the right answers, where by right answer, I mean the correct label Y for a given input X. And is by seeing correct pairs of input X and desired output label Y that the learning algorithm eventually learns to take just the input alone without the output label and gives a reasonably accurate prediction or guess of the output. Let's look at some examples. If the input X is an email and the output Y is this email spam or not spam, this gives you your spam filter. Or if the input is an audio clip and the algorithm's job is to output the text transcript, then this is speech recognition. Or if you want to input English and have it output the corresponding Spanish, Arabic, Hindi, Chinese, Japanese, or something else translation, then that's machine translation. Or the most lucrative form of supervised learning today is probably used in online advertising. Nearly all the large online ad platforms have a learning algorithm that inputs some information about an ad and some information about you, and then tries to figure out if you will click on that ad or not. Because by showing you ads that you're slightly more likely to click on, for these large online ad platforms, every click is revenue. This actually drives a lot of revenue for these companies. This is something I've once done a lot of work on. Maybe not the most inspiring application, but it certainly has a significant economic impact in some companies today. Or if you want to build a self-driving car, the learning algorithm would take as input an image and some information from other sensors, such as a radar or other things, and then try to output the position of, say, other cars so that your self-driving car can safely drive around the other cars. Or take manufacturing. I've actually done a lot of work in this sector at Landing AI. You can have a learning algorithm takes as input a picture of a manufactured product, say a cell phone that just rolled off the production line, and have the learning algorithm output whether or not there is a scratch, dent, or other defect in the product. This is called visual inspection and is helping manufacturers reduce or prevent defects in their products. In all of these applications, you would first train your model with examples of inputs X and the right answers, that is, the labels Y. After the model has learned from these input-output or X and Y pairs, it can then take a brand new input X, something it's never seen before, and try to produce the appropriate corresponding output Y. Let's dive more deeply into one specific example. Say you want to predict housing prices based on the size of a house. You've collected some data and say you plot the data and it looks like this. Here on the horizontal axis is the size of the house in square feet. And yes, I live in the United States where we still use square feet. I know most of the world uses square meters. And here on the vertical axis is the price of the house in, say, thousands of dollars. So with this data, let's say a friend wants to know what's the price for their 750 square foot house. How can a learning algorithm help you? One thing a learning algorithm might be able to do is say, fit a straight line to the data. And reading off the straight line, it looks like your friend's house could be sold for maybe about, $150,000. But fitting a straight line isn't the only learning algorithm you can use. There are others that could work better for this application. For example, rather than fitting a straight line, you might decide that it's better to fit a curve, a function that's slightly more complicated or more complex than a straight line. If you do that and make a prediction here, then it looks like, well, your friend's house could be sold for closer to $200,000. One of the things you see later in this class is how you can decide whether to fit a straight line, a curve, or another function that is even more complex to the data. Now, it doesn't seem appropriate to pick the one that gives your friend the best price, but one thing you see is how to get an algorithm to systematically choose the most appropriate line or curve or other thing to fit to this data. What you've seen in this slide is an example of supervised learning. Because we gave the algorithm a dataset in which the so-called right answer, that is, the label or the correct price Y, is given for every house on the plot, and the task of the learning algorithm is to produce more of these right answers, specifically predicting what is the likely price for other houses like your friend's house. That's why this is supervised learning. To define a little bit more terminology, this housing price prediction is a particular type of supervised learning called regression. And by regression, I mean we're trying to predict a number from infinitely many possible numbers, such as the house prices in our example, which could be 150,000 or 70,000 or 183,000 or any other number in between. So that's supervised learning input, output, or X to Y mappings. And you saw in this video an example of regression where the task is to predict a number. But there's also a second major type of supervised learning problem called classification. Let's take a look at what that means in the next video. So, supervised learning algorithms learn to predict input-output or X to Y mappings. And in the last video, you saw that regression algorithms, which is a type of supervised learning algorithm, learns to predict numbers out of infinitely many possible numbers. There's a second major type of supervised learning algorithm called a classification algorithm. Let's take a look at what this means. Take breast cancer detection as an example of a classification problem. Say you're building a machine learning system so that doctors can have a diagnostic tool to detect breast cancer. This is important because early detection could potentially save a patient's life. Using a patient's medical records, your machine learning system tries to figure out if a tumor, that is a lump, is malignant, meaning cancerous or dangerous, or if that tumor, that lump, is benign, meaning that, it's just a lump that isn't cancerous and isn't that dangerous. Some of my friends have actually been working on this specific problem. So maybe your dataset has tumors of various sizes, and these tumors are labeled as either benign, which I will designate in this example with a 0, or malignant, which I'll designate in this example with a 1. You can then plot your data on a graph like this, where the horizontal axis represents the size of the tumor, and the vertical axis takes on only two values, 0 or 1, depending on whether the tumor is benign, 0, or malignant, 1. One reason that this is different from regression is that we're trying to predict only a small number of possible outputs or categories. In this case, two possible outputs, 0 or 1, benign or malignant. This is different from regression, which tries to predict any number out of an infinitely many number of possible numbers. And so the fact that there are only two possible outputs is what makes this classification. Because there are only two possible outputs or two possible categories in this example, you can also plot this dataset on a line like this, where now I'm going to use two different symbols to denote the category, using a circle or an O to denote the benign examples and a cross to denote the malignant examples. And if a new patient walks in for a diagnosis and they have a lump that is this size, then the question is, will your system classify this tumor as benign or malignant? It turns out that in classification problems, you can also have more than two possible output categories. Maybe your learning algorithm can output multiple types of cancer diagnoses if it turns out to be malignant. So let's call two different types of cancer type 1 and type 2. In this case, the algorithm would have three possible output categories it could predict. And by the way, in classification, the terms output classes and output categories are often used interchangeably. So when I say class or category when referring to the output, it means the same thing. So to summarize, classification algorithms predict categories. Categories don't have to be numbers. It could be non-numeric. For example, it can predict whether a picture is that of a cat or a dog. And it can predict if a tumor is benign or malignant. Categories can also be numbers like 0 or 1 or 0 or 1 or 2. But what makes classification different from regression when you're interpreting the numbers is that classification predicts a small, finite, limited set of possible output categories, such as 0, 1, and 2, but not all possible numbers in between, like 0.5 or 1.7. In the example of supervised learning that we've been looking at, we had only one input value, the size of the tumor. But you can also use more than one input value to predict an output. Here's an example. Instead of just knowing the tumor size, say you also have each patient's age in years. Your new dataset now has two inputs, age and tumor size. Plotting this new dataset, we're going to use circles to show patients whose tumors are benign and crosses to show the patients with a tumor that was malignant. So when a new patient comes in, the doctor can measure the patient's tumor size and also record the patient's age. And so given this, how can we predict if this patient's tumor is benign or malignant? Well, given a dataset like this, what the learning algorithm might do is find some boundary that separates out the malignant tumors from the benign ones. So the learning algorithm has to decide how to fit a boundary line to this data. The boundary line found by the learning algorithm would help the doctor with the diagnosis. In this case, the tumor is more likely to be benign. From this example, we've seen how two inputs, the patient's age and tumor size, can be used. In other machine learning problems, often many more input values are required. My friends who worked on breast cancer detection used many additional inputs, like the thickness of the tumor clump, uniformity of the cell size, uniformity of the cell shape, and so on. So, to recap, supervised learning maps input X to output Y, where the learning algorithm learns from the, quote, right answers. The two major types of supervised learning are regression and classification. In a regression application, like predicting prices of houses, the learning algorithm has to predict numbers from infinitely many possible output numbers. Whereas in classification, the learning algorithm has to make a prediction of a category out of a small set of possible outputs. So you now know what is supervised learning, including both regression and classification. I hope you're having fun. Next, there's a second major type of machine learning called unsupervised learning. Let's go on to the next video to see what that is.